Welcome to another lesson from Unit 2.2, Applications of Newton's Laws. So this lesson is going to focus on air resistance to help you better understand and complete the lab that we are working on in class. Up until now, when you've had to solve physics problems involving free fall, so that's when you have an object falling freely with only gravity acting on it. We're often told to ignore air resistance and assume that the acceleration, which as long as you are close to the Earth, is referred to as the acceleration due to gravity with a value of 9.8 meters per second squared. So we're told that there's a constant acceleration and that acceleration is unending. That is not necessarily the case in the real world due to air resistance. Remember that this is not falling through a vacuum. Surrounding this object are billions and billions of air molecules, oxygen, water vapor, carbon dioxide, nitrogen. And as that object falls and pushes those molecules out of the way, those molecules exert an equal and opposite reaction force. Now, the reaction force that you feel because of one molecule isn't really going to affect your motion. But remember that we're surrounded by millions and millions of them. And the more air that you have to push past, the greater of an effect you're going to feel from those forces. One way to see this is by comparing the fall of a baseball and a sheet of paper. So there's my baseball and my sheet of paper. They're both dropped from the same height. The baseball is going to accelerate the whole time that it is falling, up until the time that it reaches the floor. However, air is going to have a much greater effect on that piece of paper. So here's all my air molecules. That air is going to have a much greater effect on that piece of paper. So you're going to see a much greater effect from the air pushing up on the paper, so that it's going to accelerate for a very short amount of time, and then you can even just picture that piece of paper slowly making its way to the ground. So if you were to look at their velocity time graphs, you draw these in, velocity time, velocity time. So the baseball might start at rest while I'm holding it, but as soon as I let it go, the velocity is going to keep increasing. It's going to accelerate at a constant rate right until it hits the floor and comes to a stop. We really don't see much difference in this graph because of the air resistance on this baseball. On the other hand, that piece of paper, while it might accelerate slightly at the beginning as it starts to move, very quickly reaches a constant final velocity. So this is a constant velocity just until the time that it hits the floor. So when an object is falling with constant velocity, we like to use the term terminal velocity. So terminal is that constant final velocity that it hits as it's falling. And we usually use the symbol VT. The paper reaches terminal velocity very quickly, but on a short drop to the floor, the baseball does not. Air resistance is sometimes referred to as a drag force. If you are in the automotive tech area, or if you're just into cars or motorcycles, you might have heard of air resistance referred to as drag. Experiments have been done with a variety of objects falling in air. And after collecting data and trying to find some sort of mathematical model to help describe and predict how these objects move, they've actually come across two different results. In some cases, we have the drag force, I'm going to write it as F drag, is proportional to the velocity. Other times, the drag force has been found to be proportional to the square of the velocity. Now, what does that mean? Let's take a look at the relationship on the left. This is a direct relationship. The faster you go, the greater your drag force will be. However, this is a linear relationship, which means if you go twice as fast, you're going to end up having twice the force from the air resistance. In that case, mathematically, you would find that the drag force is equal to negative b times the velocity. Why negative? Well, that's because if you have an object and it happens to be moving, let's say, to the right, that drag force is going to be working in the opposite direction to slow it down. Think about that falling object. We have the weight of it pulling it down, and that air resistance or that drag is going in the opposite way to try to balance out that force. V is the velocity, but what is B? B is known as a drag coefficient. A drag coefficient is a constant, and it depends on the size of the object as well as the shape. So you should have had enough experience with falling objects to know that the size can make a difference as well as the shape. So imagine a small piece of paper versus a large piece of paper, or two identical pieces of paper where one is flattened out and the other one is crumpled up in a ball. They're going to react very differently. Now, if you look at the relationship on the right, we still have a direct relationship. The greater the velocity, the greater the drag force. However, this is an exponential relationship because of that square. That means if you are going twice as fast, you're going to have 4 times the drag force. In this case, the mathematical relationship is that the drag force is equal to negative c times v. Once again, negative because it's going in opposite the direction of the motion. And c is just another drag coefficient that also depends on the size and shape of the object. When any object is falling, there are 2 forces acting on it. First, we have the weight. So we've talked about the weight as the force due to gravity. In everyday language, we refer to it as the weight. And it's just equal to the mass times the acceleration of gravity. The other force is the air resistance. So it's resisting and moving upwards. Once you are at terminal velocity, your velocity is constant. According to Newton's first law, the only way to have a constant velocity is to have a net force equal to 0. That means that these 2 forces have balanced each other out. 0 net force, your motion is no longer going to change. So since these 2 forces are equal, just going in the opposite direction, that means the weight is going to be equal to that drag force. Now, depending on the object, that means that the weight could be equal to some sort of coefficient times the velocity, or the weight could be equal to a different constant times the square of that velocity. Now, since some of these are constants, well, let's see. G is a constant, B is a constant, so is C. Depending on the size, shape, whatever property about that object, the mass could either be proportional to the velocity, or the mass could be proportional to the square of the velocity. So if we plot mass versus velocity, or we plot mass versus velocity squared, we can figure out which relationship is going to be appropriate for the objects that we are testing in class. In this experiment, you're going to measure the terminal velocity as a function of mass. So lots of fancy math words. That means we're going to measure values for the terminal velocity, and we're going to plot it against the mass. We're going to have some data and use that data to choose which of the two models is appropriate for the drag force of our basket coffee filters. Sorry, that's the best I could do for my drawings. So we're going to measure the terminal velocity, we're going to graph our data, and figure out which is the best model for our coffee filter. Why coffee filters? Because as you will see, they're light enough that they're going to reach terminal velocity almost immediately. So I hope you guys enjoy the lab, and I hope that this gave you a little extra background to help you understand what we are doing in class.